Thanks all for coming. So a little bit about myself. Mentioned Intellify Learning, currently Edgenuity. They're an online software company for K-12, and I'm based out of Boston. So today, what I'm going to do is give a little bit of background of our data, the way that it comes in, go over a little bit about our ETL approach that we took, and then talk about our data pipeline in general, and then how we build and deploy and run our streaming ETL jobs. So to start with, our source data comes from various education apps, and what we've done in the majority cases, we embed sensor libraries in each one that emit events or records at various points. The records coming to us are either entities like course descriptor or student or assignment, or they're events like login or navigation or assessment, like student took a quiz or an exam or something. The apps will send us entity records again when they become updated, and so events and entities kind of become commingled in a single stream. The events come to us in more or less a Caliper form. Caliper is a standard initiative for kind of unifying data that comes from learning applications, and it basically separates out into entities and events, and then it provides metric profiles for how you define things like a reading or an annotation or that kind of thing. At a high level for our delivery side of our reporting, we put everything into Elasticsearch, and then we read from Elasticsearch from a web front end that we have, as well as from Tableau workbooks and some other various things. The problem comes in when we add more than one education app into the mix, because they come with their own sets of data schemas. And so we can't write the same queries against that raw data, so we end up having to write individual customized books and reports per input source. In addition to that, we were putting everything into a single Elasticsearch index, which caused performance problems over time as the index grew large. And Elasticsearch does not do joins, and we had some key areas that I'll show in a little bit where we needed to do some joins in order to pull the right amount of data into our query tables. So as a part of our ETL solution, what we did was we created a unified set of Avro tables, schemas, sort of serving as the canonical data set of the company. We define a separate Flink job per input source, like per learning app, and each job is responsible for emitting to one or more of those Avro tables. We're also then storing the outputs per index in Elasticsearch, and also as Parquet files in S3, because we're exploring using Presto and Drill and Athena for querying in S3 directly. So here's that example of an ETL join that we needed, where our resulting table wants to have a course ID and a role, and the inbound event only has an assignment ID. And so what we need to do first is join into an assignment entity in order to get the course ID. But then additionally, in order to get the user's role, we need to join into the enrollment record, and that requires us to join on user and on organization, and the organization therefore comes from the course ID. So basically we need to have that assignment join fulfilled before we can complete the second one. So how did we do this? Well, we came up with a concept of a join registry, and our mapper classes, as they initialize, we know which joins that we need to do at the start, and so we can define each one of those. And then at runtime, we can flat map across the input source all the records that we know will be participating in a join, and then we can key off them based on all of the known join vectors or conditions, in the sense that, like, if we know that this is going to be joined on member.id or on user type, then we can extract those fields from the input record and store them as keys that we're going to then put into the Flink state and use that to fulfill joins. Here's a more in-depth look at what that join state looks like. So when we define an entity join, we define the type of entity from the input record that it is. We define relations, like this field is going to want to equal this other field. And then as we're translating entity records into joinable entities from the source stream, we pull out those keys, as I had mentioned earlier. On the other side, for records that we want to transform, each source program defines one or more mapper classes, transformer classes, that they have a flat map at the beginning that pulls in records and then emits them as transforming records that go into a co-process function that I'll show in a second, that allows us to fulfill the joins and then translate them into Avro. Here's more, this is kind of a clarifying slide showing that lifecycle in more detail. So each job provides one or more of these mappers, and the first thing a mapper does is a flat map operation, which allows it to pick out records that it knows it wants to translate, and also potentially unwind. So if a record maybe has a tags array value, and we want to emit a record for each tag as a separate individual row, we can do that here. Next, it'll go into the co-process state until it's fulfilled all of its pending joins, at which time we'll call the defined mapper function to build the Avro object. What we're doing is we're compiling Java class files from the Avro schemas and then using that as a shared library so that we can have compile time checks on the Avro building. This is an overview of the Flink job that shows how we split on record type. And we split out all the records that are type entity and push them off towards the joinable entity mapper that uses the join registry to figure out which records it wants to store for later. And you'll see here that the transforming co-process function stores all the joinable entities in a map state by joinable key, and then also stores by joinable key a map of pending joins that are waiting on that specific key. And so what happens is, as records flow through, if a new record flows through on the B side of the co-process from a joinable entity, we're able to look in that lower pending join state and pull out all the records that are waiting on that particular key and fulfill those joins, and then additionally populate the upper for future events that come through. This is an overview of the framework we created to allow ourselves to build these mapper classes and jobs with relatively low amounts of code. The main class tends to just define the source topic. So what we do is we have, in our ingest job, it knows all of the sources and it outputs to a different Kafka topic per source type. And so the main class defines one of those source types, and it gets attached to that Kafka topic. Additionally, we define one or more record transformer classes that emit a concrete Avro type. This is an example of the ETL main. We use Spring Boot as our kind of auto-wiring mechanism for all of our code base. And so you'll see here it has the Spring Boot annotation, and it defines that specific enumeration to attach to that LMS named ETL source type. And of course, the Spring Boot stuff runs when the job graph is first compiled, and then afterwards we're using serialization. Things I can call out in the actual individual record transformer. So this is an example of a record transformer for a quiz submission Avro schema. And so things to point out here are, one, it's marked as a component, so it automatically gets added to the the transformer mapper function. So that's just sort of like a nicety of this framework. We define that flat map that I mentioned before. There's a configure step where we're allowed to add our join definitions into the transform context, as well as specify if it's an update or an append. And then finally, this is that mapper function that actually takes the source record that has had all of its joins fulfilled and maps it into a quiz submission. This is a detailed example of what a flat map tends to look like. It pulls a record out. So all of our records come through as JSON. And so we've got a bunch of helper functions for processing and pulling out property values and things that are nested. And so in this case, if a record comes through that has an event.type of outcome event, then we're going to send it along as a transforming record. In diving deeper into the context configuration, you'll see here that we're defining two joins that happen one after the other, and this is related to that earlier example I showed. So first, we're joining on assignable digital resource, where that digital resource's ID is equal to the event's assignable.id. And then what we're going to do is we're going to take that digital resource and we're going to append it into the event object under the field activity. And then once that join is fulfilled, we're going to look for a membership entity, and we're going to join on those two fields. And then once we have that record, we're going to store that in the source record under the field enrollment. And then we're going to, this specifies that we're going to use the mapper that's included in that same class. And the mappers usually look something like this, where we start with the Avro compiled class, and we pull in all the record values that we need. And at this point, we've got all the values that we're looking for from the previous joins. So we use in Elasticsearch aliases, an alias per Avro table to define kind of like a logical table view over multiple sources. And so because each source job outputs one or more of those tables, but under the same schema, we're able to combine them under a single unified view that we can then query against directly without having to know the internals. But what that also allows us to do is iterate on the job, deploy a new version of it, and then once it's caught up and we verify that it's correct, we can swap that out in the alias with the new version. Or if we wanted to remove a source directly, we could just remove it from the alias and not have to worry about doing special deletes in Elasticsearch. We've also created a bootstrapping source that allows us to seed data from our S3 bucket. We store data, and I'll show this in a future slide. We store data in an S3 bucket ordered by hour-wide partitions by event time, and we're able to stream that through. And then we have a source function that seeks our Kafka consumer to the end based on where it found your range ends, and it switches over from the one to the other. And this is kind of an abbreviated example of what that tends to do. In this particular case, I've added an arbitrary sleep to get the alignments to work right. It's not necessarily 100% accurate. There will be some cases where there will be some overlap, but we can deal with that with event reordering. Here's an overview of our data pipeline. We have a REST service that accepts all the incoming events across the entire spectrum, and that assigns a unique hash to the record based on the string value of the contents, and it sends it along to a single ingest topic. We've got some jobs that pull data from various sources and jobs that push, but everything goes through this one collector service and therefore into the one ingest topic. We have a Flink job that reads off that topic and does some dedupe, and then it additionally pushes out into Elasticsearch for kind of more real-time querying on the raw data. It pushes into a bucketing sync into EFS because the bucketing sync doesn't support S3, even though with Flink 1.6 now there's a new one that does, so that's exciting for us. It pushes into what I've called here the ETL source sync, which does that routing to a specific Kafka source based on the ETL source, which allows us to bind to the ETL jobs down the road. And then a dedupe hash sync. So I added stars here. The dedupe filter and the hash sync rely on the two-phase commit that came in with Flink 1.5 to allow us to do exactly once dedupe with Redis, whereas otherwise, if we had an issue and the job failed, it's possible that we've updated the Redis dedupe table and then therefore would ignore records that come through after we recovered. We have a job so we store data in EFS in ingest time. When we first do a big load of our data, we get data back from 2014. And so I found that when we were trying to bucket into event time buckets, we would have tens of thousands of buckets open at once, which would cause the checkpoint state to never succeed, and we would always time out over 10 minutes. So switching that to ingest time buckets allows us to kind of constrain the number of open buckets at once for the bucketing sync, but it also requires us to have a job to translate those files from ingest time to source time and then update them upload them into S3, merging them with the existing records that are in S3. And these are the records that are streamed back through in the bootstrapping source. This is a kind of an overview of what I described earlier with the ETL sources. We have a processing task, or a processing group in our pipeline, which basically utilizes some nice features of Flink, like sessionization, for figuring out things like time on task and concurrent active session reports that we do. And in the future, we're hoping to use CEP to do things like detecting cheating and stuff like that. And then, as I described earlier, for delivery, we're using Elasticsearch mainly, but we're also exploring using the data that we're writing out in S3 with Athena and Drill. In our deployment model, what we've done is we've created a couple of abstractions. We've created the concept of a data stream app, which is what's built in CI and versioned, and it's deployable using our deployment service. We created a deployment descriptor format for it, which I'll show in a second. Instances of those are started by our data stream service, and those produce output to namespace syncs, so that when you start two instances of the same app, they don't clobber each other's output data. And that's how what I described earlier with the ETL process, how we're able to iterate on those ETL jobs by spinning up multiple instances and then seeing that they output into different namespaces that themselves become more or less immutable, where you're not going to have a separate job that's writing into the same data. This is a graphical overview of our deployment model. When you make a change, we do a CI build for it, and then you can deploy that version to QA or to production, and then you can start an instance of that. I'll show the graphical UI that we have in place for that. This is the deployment descriptor example for a data stream app. This is for that hypothetical app that we've seen earlier in this talk. You'll see that it's defining itself as being multi-tenant and versioned and supports seeding of a specific type. This is a screen cap of our deployer service actually deploying that app. You can see the existing version and the new version. Here's a show of our management UI for data stream apps. You'll see the two that are deployed to this specific stack. One is running, one is not running. when you go to start an app, if it supports seeding, you're presented with a range of all the data that we know for that particular seeding type. And you're able to specify parallelism and things like that. The UI shows a graphical representation. What I found is this can sort of be more informative than the one that appears on the Flink UI, because that one collapses all of the operators per particular task manager slot, whereas this one kind of sprays it out. This was adapted from the original Flink job renderer from the Flink website. And then we show a history, so jobs can cancel and restart for a particular job instance, especially when it's a singleton instance like this one. And we send certain parameters to our jobs in order to allow our service to control them, and then we read back those parameters, things like unique ID. So for a singleton, we say data version is unversioned and the unique ID, whereas in this case, we have a different data version. Here are 3 examples of Prometheus queries that I like to use to monitor things. Ingest rate, last checkpoint duration, and then an interesting one is full restarts. So if a job restarts, and usually that happens because a task manager oomed or it lost Kafka connectivity or whatever, when you go to look at it, it'll still be running, but it has restarted, which means there's usually something that'll appear in the exception tab for you to look at. And we have these on Grafana, so it allows me to see right off if our collection rate and our ingest rate are matching up or if we're going to fall behind. I send heartbeats into our queues, and then we have a tracing filter that emits a metric based on that timestamp and the current timestamp that allows us to measure lag, and lag is an important characteristic that we have. And yeah, you feel free to message me on Twitter if you have any questions. Or
are there any questions?
Can you explain a bit more how the bootstrapping stuff works? Particularly how you read from S3 and kind of keep it the same as in Kafka, I guess? Do you read it in the same order that you saw it in Kafka, or is that not relevant to you?
So we read it in source time order. That's why we've arranged it in that way.
So you read it by date and then you switch to a Kafka topic on an offset that you get from the records, or?
Yeah.
Yeah. Okay.
Other questions? Okay, then thank you very much.